Hello everyone, my name is Ankur Das. I'm a graduate student at University of Kentucky. Today what I'm going to present about is the effect of a uniform magnetic field in a graphene lattice. I'm doing this work for almost 1.5-2 years with my advisor Dr. Ganpati Murthy and my co-advisor Dr. Rivu Kaul, and we have uploaded some of our findings on archive, and it's under the review process in PIB, and hopefully we'll publish very soon. And we are hoping to publish and put out our other findings very soon in this month probably. So in this talk there are two main sectors. I'm first going to talk about the effects of non-interacting graphene in magnetic field, what happens there, and I'll always explain why that is interesting. And then I will go for a little bit more interacting pictures and talk about that what happens there. So the interacting picture is supposed to come out very soon within this month, and the non-interacting picture is out on this archive number if you want to take a look. So first the non-interacting part. So let me remind very quickly that in a non-interacting lattice what you need is magnetic translations, which will commute with the Hamiltonian, but the magnetic translations don't commute with each other if there is a uniform magnetic field. So if you have a P over Q flux per unit cell, I wrote 1 over Q here for example, but you can have P over Q, then you need to increase your unit cell Q times, and that way the different translation operator will start commuting with each other as explained in the first point. But in a magnetic, in a graphene lattice, if you do that, the number of sublattices becomes 2Q, and now you don't have a 2-band problem rather than a 2Q band problem. And it has been quite well known for the Landau levels in graphene. When you put a very low magnetic field, you get doubly degenerate Landau levels. You get n equal to 0, plus minus 1, plus minus 2 Landau levels, and they're not separated like a quadratic band problem where they're separated equal distance. Here they are separated at square root of mod n. So the energy of some nth band will be square root of mod n, and for the each band the Chern number will be 1, that one can show, and this is the regular Landau level graphene picture. So we expect that if we take our problem and take a very low magnetic field limit, we should end up there. And this is the Hamiltonian problem that one has to write down. The hopping Hamiltonian is written in a very specific gauge where only one bond picks up the phase, and this gauge is known as the optimal gauge. So as you can see in this picture, there are 0, chi-naught, and so on and so forth, and this chi-naught is 2 pi over Q. Okay, so the locations of the Dirac points can be solved in this gauge very easily. You can write down the zero energy problem of the lowest Landau level system of the nearest neighbor hopping problem, and you can see that the lowest Landau levels, which is the 0 Landau levels, have 2Q Dirac points, and those 2Q Dirac points are pointed out by this point. But what we are excited and interested about understanding what these 2Q Dirac points specify is that these problems, how protected they are, and we want to show one phase diagram which shows that there is some non-triviality in there. So basically you have two different kind of hoppings. Now only the nearest neighbor and the next nearest neighbor, and we also put a staggered potential, and we can see there is a competition where the central band total Chern numbers actually change. And basically what happens is for Q equals to 5, if you fill up the half, if you have the half filling, then for V T2 going to 0 limit on this line in this pink regions, this is a non-topological state. So the half filling, the total Chern number is 0, but on the either side of this blue and this golden region, the total Chern number is plus minus 5. So one side is plus 5 and one side is minus 5, and this happens, as you can see from the picture, that exactly on these boundaries half of the Dirac points close and the half of the Dirac points get opened. Okay, so now the natural question is that what are the symmetry constraints that preserves this Dirac point, and that is our contribution to this study. And basically we showed that as every T2 sends Kn to Kn minus 1, and the R pi, which is the inversion operator, and there is a C3 or R2 pi by 3 which rotates about the center of lattice 120 degree, these three rotations with the chirality. So it turns out that chirality is protected even if the time reversal and particle hole are broken in a magnetic field, uniform magnetic field situation, but the chirality is still broken, preserved, which makes sure that there is this structure of the Hamiltonian written in the sublattice space. So this is AB space. And we can show that these degeneracies are protected by understanding that the zero energy eigenstate, one can write down zero energy creation operator and annihilation operator, and can show that the R2 pi by 3 must become a sum over zero energy states. And you can project down this R2 pi by 3 into one Dirac point, and that Dirac point you can show that the RA/RB must have a same eigenvalue if the this eigenstate is the eigenstate of the system, and that explicitly you can calculate this RA/RB of n and can show that their argument doesn't go to 0, which you expect if RA/RB dagger determinant argument is non-zero, which means that all the eigenvalues are not same, which we expect for zero energy, non-zero energy state. So our initial assumptions is wrong, and we can show there's a zero energy. And one point I would like to mention that we can open this gap by two different ways. So we can preserve the chirality and try to break the translation symmetries. That will open up a gap, but those gaps will be all trivial gaps because there's an A3 classification, and if we translated the whole system into chirality broken part, which, let's say, for example, if you had a next nearest neighbor hopping, it breaks chirality, and you can see that there's a topological state and it depends on the magnetic flux, and you can go to Z classification, which is exactly given by Kitaev's model. Okay, so let's go to the interacting theory. So the Graphene's quantum spin Hall was previously observed by Andrea Young and company when they used a very hard in-plane magnetic field and saw that the two-terminal conductance actually jumps from, at nu equals to 0, jumps from 0 to 2e square over h. And that is exactly what is presented here. As you can see, the in-plane magnetic field was increased, and as you keep increasing the in-plane magnetic field, at certain point there is a transition. Of course, it looks like the transition isn't certain, and the reason I would suggest is that this transition is at finite temperature. It's supposed to be in zero temperature, then it will be sudden, because in 2D you expect that to happen, but there is a transition. And this transition is not completely unheard of, because Kharitonov actually did predict this transition from his phase diagram, where he explained that if you add a sublattice, or in this case, if you have a zero lambda level in this case, you can get Valley asymmetry term. And then there is a ferromagnetic phase, which is this blue region, and there is an antiferromagnetic phase, which is this green region, and there could be a transition by changing the in-plane magnetic field, and that is exactly what Kharitonov expected. But there has been a few studies where people have tried to understand what these magnetic fields are and how they give different phases, but the bond order phase was never seen, which was predicted in the continuum limit, but none of the lattice understandings have shown that is true. Okay, so we actually saw that, okay, can we reproduce this story in a lattice scale interaction? So what we did is that we understood this UZ and U perpendicular, these two fields. What one can do very easily is that do a phase rearrangement identity and can show that you can write down it as a spin-spin interaction, and that is exactly will be nearest neighbor Hubbard interaction and the nearest neighbor spin-spin interaction type interaction, and that is exactly what we did. We used this specific two interaction, a Hubbard and the nearest neighbor spin-spin, and so this is the Hamiltonian, just to show. And what we did is that we did a self-consistent Hartree-Fock, assumed that the Kekulé distortion phase that was found in the continuum fits in the unit cell, and we assumed these parameters. And what I'm going to show you is the phase diagram of this. And we did see that for very large Qs. We did for Q equals to 12 of 2, but I'm just going to do the 6. So we see the antiferromagnet phase, but there is some bond order inside it, and as you go far and far apart, this bond order phase dies off. We can see that there's a Kekulé phase, which was not observed before, but we can see that in this theory. And there is a columnar order phase, there is a CDW, but this extra bond order phase was not seen in continuum, which we see here, and this bond order phase is exactly what you see. This is what we call the tricolor bond, because you can see there are 3 types of bonds that are here, and these phases appear for all Q's except for the Kekulé phase, which we did not see for Q equals to 3, but we see all the different phases. But there are some intermediate phases, and they look like more dependent on the unit cell and how you break those unit cells, but these big phases are present almost for all Q. Okay, so I'll conclude, put the conclusion here and try to point out the main 2 factors. So we described there are 2 possible gapping outs in the non-interacting limit, and we showed that in interacting limit, if you actually write down this theory, you can write down Kekulé, CDW, all order states, and we see a tricolor and SDW and a columnar phase, which was not seen in the continuum. We are planning to have some experimental evidences which we are talking about, and I will happy to talk to you anyone in future if anyone wants to talk about it. So there are some future plans which partially field band techniques, finite system problem, finite fractional filling problem. These are all in plan which we are planning to do, and the stability with the long range. These are all in the plan. So I would like to thank the supporting NSF for supporting this project, and thank you all for listening to me.